All right, hello everyone. On behalf of Forge College, I am absolutely thrilled to be your guide for this explainer. If you've been following along in our series, you know we're right in the middle of a massive architectural transition. We are taking your hard-earned Ethereum virtual machine skills and upgrading them for the high-octane environment of the Solana virtual machine. Think of this as taking your familiar engineering blueprints and translating them into a completely new high-performance format. Today, we're focusing on a really crucial piece of that puzzle: modeling and emitting events in Anchor. Events are basically the critical bridge between your on-chain logic and off-chain reality, right? They're how your smart contracts tell the rest of the world that something important just happened. But as you're about to see, the way we build that bridge on Solana is fundamentally different from what you might be used to.
In our previous lesson, we mapped out Solidity event semantics and patterns. Here's our quick schematic for today's explainer. First, welcome to Anchor events. Second, the index topics dilemma. Third, engineering workarounds. Fourth, translating a transfer event. And finally, our key takeaways.
Let's jump right into Section 1. Welcome to Anchor Events, new blueprints for the SVM.
So when you make the leap from Ethereum to Solana, there's a bit of a culture shock waiting for you in the logging department. Ethereum's event system is a lot like a set of flexible filing cabinets. You toss data in, tag it with nice little index cards, and your off-chain apps can just easily pull it out later. Solana, however, uses a highly structured, blazing fast logging system. It's less of a filing cabinet and more of a raw, high-speed data stream. On Solana, the Anchor framework represents events simply as Rust structs, and to make it work, we rely on two main primitives. First, there's the event macro. In Rust, a macro is basically just code that writes other code for you. When you apply this to a struct, Anchor works behind the scenes to automatically generate all the necessary serialization boilerplate, so you don't have to manually encode byte arrays. Second, we have the emit macro. Notice the exclamation point there. That tells you it's a Rust macro, not a standard function. This is your trigger. It performs the actual serialization and runtime logging, writing those packaged bytes directly into the program execution logs.
Okay, let's talk about that serialization process for a second, specifically Borsh serialization. When that emit macro fires, it uses Borsh to encode your event data into a highly compact binary format. To really grasp this, compare it to something like JSON. In JSON, every piece of data is neatly labeled. You literally send the text name right next to the value Alice. Well, Borsh doesn't do that. Borsh completely strips away all the labels to save space. Imagine Borsh as a tightly packed, heavy-duty shipping container. To maximize speed and efficiency on the network, every single item in that container is packed strictly in the order it was declared in your struct. Because it's a raw binary format, there are no labels on the inside telling you what is what. It is just a stream of bytes. So if you pack a shirt and then you pack shoes, the person unpacking the container on the other side must know to pull out a shirt first and shoes second.
Which brings us to the absolute golden rule of Borsh serialization. Field order is not cosmetic. It determines the byte layout. This is an incredibly crucial engineering constraint. Let's say you're reviewing your code 6 months from now, and you decide to clean things up. You alphabetically reorder the fields in your event struct just to make it look a little prettier. Well, congratulations. You've just metaphorically exploded your off-chain decoders. Think about the disaster scenario here. Your front-end application expects a 32-byte public key first. But because you reordered the fields, it instead reads an 8-byte transaction amount and combines it with random adjacent memory. It's absolute chaos. Any historical listener or database that assumes the old layout will just read total gibberish. If you must add new fields to an event in a future program upgrade to maintain compatibility, always append them at the very end of the struct.
Moving right along to Section 2, the indexed topics dilemma.
Okay, so we know how to pack our highly efficient binary container, but what happens when we try to actually search for a specific package in the stream? This is usually the most jarring realization an EVM developer is going to face. You are inevitably going to look at your Rust code, scratch your head, and panic a little bit asking, wait, where on earth did my index topics go? In Ethereum, life was great. You just slap the word indexed next to a parameter and boom. Under the hood, Ethereum pushes that data into special, Bloom-filterable topics inside the transaction receipt. Tools like the graph can filter millions of transactions instantly. Well, take a deep breath, because on Solana, those native, beautifully filterable index topics simply do not exist. Your easy search tags are gone, and your events are just serialized blobs floating in a blindingly fast stream.
If we map these two ecosystems directly against each other, the differences are pretty stark. In Solidity, index topics are a native yes. In Anchor, it's a strict no, and you have to engineer your own solutions. The payload mechanism shifts from an Ethereum event log to our Borsh serialized struct, and the trigger simply changes from the emit event function syntax to the emit macro.
The crucial point here is that while the payload and the trigger concepts map over quite logically from your EVM days, the searchability part requires an entirely new approach. We literally cannot natively filter a transaction log by a sender's address anymore.
So what do? That brings us to Section 3, Engineering Workarounds.
Now seriously, don't panic. As engineers, when we lack a native feature, we just build it. We have incredibly robust architectural patterns to replace Ethereum's indexing capabilities and make your fields efficiently queryable once again. Basically, you have two primary options here, depending heavily on your project's needs. Option 1, write your searchable keys to a small index account, a program-derived address, or PDA, at the exact time your event happens. Why do this? Well, it's perfect if another on-chain smart contract needs to query this data later. It costs a tiny bit of rent to store the data on-chain, but it makes direct queries incredibly fast and accessible. Option 2, put all the rich details directly in the event payload and rely entirely on a custom off-chain indexer. You build a service that scans the raw logs end-to-end, decodes those Borsh blobs using your layout rules, and builds its own searchable database. Why choose this route? Because it preserves a tiny on-chain footprint, saves your users from paying storage rent, and pushes all that heavy lifting to your off-chain servers.
Let's look at a real example in Section 4, translating a transfer event. All right, enough abstract theory. Let's bring this down to earth and see exactly how this translation works. We're going to take the classic, totally familiar ERC20-style transfer event and re-engineer it. You probably know this one in your sleep. In Solidity, you write event transfer passing in the address indexed from, address indexed to, and a uint 256 value. It's elegant. As we discussed, those indexed keywords historically told the EVM to put the sender and receiver into the searchable Bloom filters. Your front end easily queries all transfers from address A, and it just works seamlessly. Now let's execute the anchor translation. We declare our transfer event struct and tag it with the event macro. Our data types actually have to change to match the SVM. Instead of address, we use pubkey, which in Solana is fundamentally just a 32-byte array. Instead of uint 256, we use u64 for the amount, which is pretty standard for representing token balances on Solana. Notice the glaring omission here. There is absolutely no indexed keyword anywhere. Everything is just packed directly into the struct. And let me reiterate our golden rule one more time. If we ever wanted to add a memo string to this transfer event in version 2 of our program, we absolutely must put it below amount. Otherwise, our Borsh shipping container will unpack backwards for all our legacy indexers.
And finally, how do we actually pull the trigger on this? Inside your program instruction, you have to gather your variables. Now, unlike Ethereum, where msg.sender is just globally floating around in the ether, Solana requires all interacting accounts to be explicitly passed in to the instruction's context. So you grab those specific pub keys from your context accounts and you execute emit, passing in the transfer event populated with from, to, and amount. That single line of code triggers the Rust macro to handle the runtime serialization and writes the raw byte blob straight into the Solana transaction logs. If you built out our earlier workarounds, you either also wrote those public keys to a PDA in that same instruction, or your dedicated off-chain server is aggressively listening to the network, ready to catch this exact blob, decode it using the structs layout, and drop it right into a traditional database.
All right, wrapping things up with Section 5, key takeaways.
Transitioning your event logic from the EVM to the SVM requires a really massive shift in how you think about data structure versus data searchability. So here are the core rules to finalize your blueprints. First, declare your structs with the event macro to generate the boilerplate and fire them off with emit. Second, respect the Borsh serialization. Field order is strict. It is not cosmetic, so always append new fields at the bottom. Third, because you don't have indexed topics, you've got to actively architect your own searchability using PDAs for on-chain queries or custom off-chain indexers. And finally, always document your event layouts in your IDL. The IDL, or Interface Definition Language, is literally the Rosetta Stone for your smart contract. It tells your TypeScript front-end exactly how that Borsh container was packed. If your IDL is accurate, your off-chain developers won't have to guess your byte layout, which saves absolutely everyone a massive headache.
So you've successfully modeled your highly efficient events, you've packed your binary containers and sent your logs streaming out into the world. But it begs a bigger question, doesn't it? In a truly decentralized, high-speed system, what happens to your state when the blueprints fail and errors are thrown? Are you ready to handle the fallout? Well, that is exactly what we're going to tackle next time when we dive into error handling patterns, mapping Solidity reverts over to Anchor's robust error systems. On behalf of Forge College, thank you so much for joining me for this explainer. If you want to dive deeper into this subject, get your hands on some code, and explore plenty of other fascinating Web3 topics, make sure you head over to forge.college. Keep building, keep learning, and I will see you in the next one.